Yeah. Still empty.
At least you still have 2 minutes. That's quite fast. Also, the quiz should already be published, so you don't have to wait for the bell. So you get your 15 minutes anyways. If you are eager to start. Good morning. Can you access the quiz? It should have been published at 10:15. And there should be 3 questions. I have no viewer on YouTube. There goes my green thing. can we o'clock you should be locked out of the system if you started at 10:20. So you can continue. After 15 minutes, you're going to be kicked out anyways. But I'm a little bored over here. So I'm going to start talking to the ones that started in the beginning. So, yes. So what we're doing today is going to talk about Chapter 6, up to the one we didn't get to last week. And we're going to hopefully get to being in sync with the lecture slides. I'm not sure. It's fine. We're going to have enough time to catch up with the recitations to the lectures before the midterms. So we are still deep in mechanics, but we're getting towards the end. Remember, we're only getting to chapter 12, and then we're moving over to chapter 23. So that means we're almost done with mechanics. That means we're almost approaching midterms. So what we've done last time is we introduced Newtonian mechanics. So we went and said that the reason for an acceleration is force, and the thing that keeps stuff from accelerating infinitely, stuff speeding up infinitely, is mass. Mass is kind of like keeping acceleration or determining acceleration at a certain force. We said Newtonian mechanics holds only in the inertial reference frame. That's not very big limitation. And we said that if there's no force, then no acceleration. If there is a force, then mass times acceleration. It's actually not quite correct. That's not what Newton said. But we're going to keep it at that for now. We're going to get back to one case in the end where it doesn't work. Because what if the mass changes with acceleration? And we were saying third law is that we're interested in force between pairs. And so we introduced additional forces and for kind of forces that we need to simplify complicated systems. And we introduced tension. Tension is a property of an elastic material, and normally there's two things happening under tension. Something stretches, and tension gets propagated to the end of the rope, for example. We're assuming that there's no elastic behavior of the string. Instead, what we're having is simply plastic material. And so that means that tension in one part would be propagated to another part without getting smaller or getting bigger, because we're also assuming that the rope has no mass. So it means that it does not contribute to acceleration or to gravity or to any other. And so why do we need tension? Because you can try and solve this problem with breaking down the forces into components. You're not getting far, because this one is arrested with that one, and so that means that if you're pulling this one slides sideways, right? It's not pulling up. You pulling this down does not pull this one down. It moves it at a slight incline. So this is a weird arrangement, but that's what mechanics is about, right? We're doing mechanics currently. It's all about these little contraptions. So what we want to know is where's it going to slide? We would say, well, the mass of this is smaller probably than the mass of that. You see this is 3.7 and the other one is 2.3 kilograms. So clearly this one should move down and this one should move up, right? But that's not the case at an incline, because we introduce a second systems force, normal force. Normal force would keep this thing from sliding down. It just lets it go sideways, right? And so that means that its gravitational force is not pointing this way. Well, it's still pointing this way, but the resulting force is less. If this was flat, then there would the normal force would be opposing all of gravity. So that means that if this angle was small, then this force, the resulting force is small. And the angle is 30 degrees, so that's pretty small. So I wouldn't venture a guess. I would not know if this one is pulling this down or this one is pulling that down. So you're going to figure that out. And I'm also interested, so that's E, basically, and A, the magnitude of acceleration of each block. You don't have to do C potential in the force. All right? So find your group, start discussing, 5 minutes, and then I'm going to start throwing random thoughts at them. You remember how it works, right? Turn around. Now is the time that you can actually talk to your neighbor. That's the difference to a quiz. You're not supposed to talk to your neighbor. Just to, I don't know, find that out. minutes, 5 minutes are over, just kind of throw random thoughts at you. So you can listen to me, but you don't have to. You're already ahead of them. What I would start with in these three body diagrams is drawing all the forces that I know. And mass times acceleration that I expect. So the forces that I know would be normal force. And you're asking, why does a normal force act on the top of my box? But remember that these boxes are not what we're considering, right? We're drawing them to just, I don't know, make a cartoon. But in the end, we're only considering a particle. So it's just, it looks nicer. I should have just drawn a single particle. Then the force, the normal force, would be acting on that particle at a 90-degree angle with respect to the surface, right? So this is my normal force. What else is acting? Gravity. And am I missing something? The string, right? Otherwise, it would just slide down under its own weight. So the string would be exerting tension there. So, all right. So the resulting force, the resulting acceleration might go down that direction. Might go up. I'm not sure. But if it goes up, then I will just get a negative acceleration. So I will just point it that direction. And now I will do the same thing in this direction. I have tension, and I have gravity. Ft for up to 2, Ft for up to 1, N1, T1, T2. Anything else, normal forces means, imagine it was hanging on that, this wheel was like a little bit shorter, and there might be a normal force that direction, but right now we have a gap, so that's good. Also, if there was a normal force that direction, it would just kind of make it like grind on it, right? This would cause friction, but we are told that we don't have to worry about the friction. We don't have to worry about friction. So, anyways, no normal force on that. So that's not good. I have a lot of arrows. Yes, this acceleration goes up maybe. So I have a lot of arrows. And the annoying part is they're going in all different kinds of directions. Right? So I have gravitational force there, tension in that direction, normal force in that direction. So what do I do? Break it down in components. Right? So I break down the first particle into components, and I break down the second particle into components. And so what I will do is the x are in I direction and in j direction, x and y, right? And so in I direction, I have tension times, if this angle was 0 degrees, it would be all in that direction. So cosine angle. Yes, I have minus n times a in the opposite direction. And I have this component of the normal force plus arrow shorter plus f normal force times zero. Why is it 0? Because all of them according to their according to their orientation are on one side. And then in j direction, I will just have ft1 in one direction, that's minus y direction, plus f normal times cosine theta. Cosine because the angle was the angle of sine theta. So here this would be for particle 1. For particle 2, I would do the same thing. What's the forces in I direction? None. A direction, I get gravitational force down, and mass 2 times acceleration 2, acceleration 1 would stay consistent with everything on one side. Plus 2 0. So how is that helping us? Well, it helps us with several things. We can make simplifications. The first simplification is this T1? Is there one tension in this direction and a different tension in the opposite direction? Like, is there more tension going into the rope than coming out of the rope? There's not, right? It's the same tension. This is T. This is T. So that means I could solve this one for T and plug it in there. Now I can plug that one in here. But the other thing I would like to do is get rid of normal force, because I don't know the normal force. I know that the normal force is just big enough to keep it from falling into the plate. I don't know anything else about the normal force. So I can plug that normal. I can solve this one for normal force, and then plug that one in there. That one in there as well. And then I can plug it in there. I can put all of them together in this one. I'm having trouble because I have a cropped screen, so I have to stay in this area. So I can put everything together and I have gravitational force 2 minus m2 a2 times cosine theta minus m1 a1 plus force ft cosine theta. What were we interested in solving? We wanted to get A, right? A is the increase in velocity, and this one get faster than that one go. Like, imagine this one was pulling down. Would this acceleration be different from that acceleration? It should not, right? They're connected by a string. That's what keeps them in a system. So we can make another connection. This is the same acceleration. So now all we have to do is solve for acceleration, and we're done. Give it 2 minutes. Actually, no, it shouldn't be 2 minutes. I did everything, so you had the chance to do it in parallel. So this is how I would have done it. Now, just for my own record, it's 10:53. Because so what I'm doing is, if you have written your answer in the recitation chat group before me saying that on video to myself or my TA, you're getting points. Now it doesn't make sense for you to type it in after I give you the solution, right? So it's 1054, you can still put it in. And if it's 1055 and I give you the solution, basically that's when the gap falls. Right, so we would simply solve for the acceleration, and we're getting 0.7. And apparently, so we got a positive effect. In our case, we would have gotten negative acceleration. And the way that I set it up here was I flipped the acceleration towards t. So anyways, it goes up. The bigger block on the incline will just slide up. So the little block is moving the big block up. Little block moves down, the big block moves up. Also, I'll make this available so you can check it out. Right, so that gives us one strange observation, and that is, how come that little block can move that big block? Right? That's not what we're seeing in real life. Many things will just hang and hold, right? So that's because we have considered frictionless surfaces, ice basically. And so we're introducing new forces. And so the forces that we're introducing now are friction and drag. Friction is the interaction between two surfaces that slows stuff down, and drag is the interaction between a surface and a gas, or a liquid, or fluid, that slows stuff down. And you already read ahead, so you know that friction has a very simple formula. But friction is a very complicated research area. And the research area of friction is called tribology. And it's important, you can imagine, because people are estimating that about up to 50% of all the power of your car is actually just going into making your motor move. Not making your wheels move, just keeping your motor from grinding to a halt, basically. So that means if you could just lubricate it better, or make a material that doesn't require as much energy to keep it pushing, it would save you a ton of money, right? So tribology is a big deal, and the weird thing is that even though we have invested a lot of energy into research in that area, we still don't understand a lot. So from a simple point of view, you might say, well, a surface is rough, right? And so if you have two rough surfaces, you kind of have like a registration. Registration means it sticks in between and it doesn't want to go over until you put enough force on it to make it jump to the next hill or something. But that would mean that all we have to do is make the surface more flat, right? But we find that, people find that if you make metal surfaces extremely flat, we can make stuff really flat just by grinding with smaller and smaller particles. They weld together, meaning they are completely, like the friction is basically infinite, or really, really high. So making it flat doesn't work. So it actually turns out that there is like an optimal shape where that your surface should have for it to sustain sliding. And that's not like little, little bumps. Well, it's kind of like, maybe it's like goosebumps. It's like really tiny bumps. They're atomically small. So there are some materials that give you a very small friction. For example, graphene, the material I'm working on, gives you a process called superlubricity, meaning it's super lubricating. It doesn't need a lot of, it needs almost no force to move. So the weird thing is, even though this mechanism for every material, for every surface is different, people found that the force to overcome friction just depends on the normal force. Basically, if it's a flat area, like a flat surface, just depends on gravity. So this is weird because we were just saying every surface has a different mechanism of sliding. How come they are giving us the same relation between them? All the complexity is in this coefficient. So up till now, we cannot predict, we cannot use computers to simulate the friction coefficient. We cannot calculate, okay, so now imagine I wanted to make a new material, what would be the friction coefficient? Because then people are like, well, you have to consider individual atoms because they are the protrusions, but you also have to consider the whole surface in which you're interested in. And so we cannot calculate that. So these ones are empirical numbers. Basically, there are people that just take stuff and slide it on top of each other and see how much force it takes. The other weird thing is that we're having two different kinds of friction. One is static, meaning the one that has to be overcome to move something, and the other one is dynamic or kinetic, that you have to keep adding force to keep it from slowing down. So, but both of them have the same functional dependence. So this is with a static friction coefficient, and then this one is with a kinetic friction coefficient. You see, all the rest is the same. So you're getting, for every material system, you're getting two friction coefficients. A big one, that's your static one. You first have to put in a lot of force just to make it start sliding. And then a smaller one to keep it sliding. So there are like weird questions come up like, does it slide? You're like, well, the dynamic friction coefficient tells me that, yeah, sure, it's the acceleration. But you have to still consider, does it even start to slide? So you have to start with considering the static friction coefficient first. So that's why we don't like friction. Because friction is complicated to calculate, and we don't really understand where it comes from. Right? With gravity, we're like, well, mass is attracting more and more about that. We can calculate more. Once we understand the concept, we can go from there. For friction, basically, every time you get a new surface, a new shape, you're getting new mass. So this is an interesting problem. In Death Valley, the hottest place, is it still the hottest place? I think it is, even for after global warming, it still is the hottest place in the world. Death Valley, and they have racetrack. So it's like a dried out lake bed, and in there are stones. And behind the stones are tracks. So people found that these stones are moving. Right? There's nothing wrong. Okay, this is Death Valley. There's nothing there. There's no animals that are messing up your observation. There's no people. So the weird part is, why would they slide? And so you understand, like aliens, or I don't know, metaphysical magnetic fields. There's a lot of conspiracy theorists out there that are like, oh, racetrack flying. That proves something. And then that something is normally what they believe in. So anyways, what I want to know is how much force would it actually take to move an average stone, maybe 20 kilograms, around? Is it just a tiny bit of force, basically? Is it just, I mean, there's still rain happening there occasionally, and there are earthquakes, maybe that's what makes them move. So how much force does it need? Oh. You have to give me a number. Because the next part is going to be, is wind enough to move it, right? Because that would be my hypothesis. It's just wind blowing in one direction. So go, calculate the force. What I've given you is friction, the coefficient of kinetic friction of about 0.8. So how much force would be needed to keep it moving? So how do we start in the free body diagram? We put all the forces. Gravity. I should call it weight for gravity. Force. Direction of motion. This is kind of weird, right? How does a stone know where I'm moving? Because it's always opposed to that. Okay. So what? We have to do I and J. I. In I direction, I have kinetic friction. And Y direction, I have T minus Y. Doesn't excel. Okay. So this one in and in there. I just have to put in T. It is 1108. It is 978. Oh, 116. Is that a lot? A lot. It's like the gravitational force of 16 kilograms. You can lift 16 kilograms, or you can, I don't know, pull 16 kilograms sideways. But it's still, like, it's, you would not expect that wind might be able to do that, right? So we'll see. What do we need to calculate wind? What kind of force is wind exerting onto a stone? If I were to add something into my free body diagram, what is that force of wind? That's my hypothesis. Wind moving, right? So the question is, what kind of force does wind provide? How does it interact with it? And it's a different kind of friction. We call that friction between a fluid, between gas, right, and a solid, drag. So drag force is a force that is depending on the wind speed, depending on the density of the material of the fluid, right? This one is like 1 for air, but 1,000 for the water. So water would exert 1,000 times the drag. That's why it's hard to swim, right? So this is the wind velocity. This is the wind density. This is the shape, and this is the cross-sectional area. So if you wanted to build a car that can go really fast, you have to minimize the force that keeps it going faster, right? So if you want to make something that is really narrow, has a small area, goes through air, not through water, maybe goes through vacuum, right? If you were to go through vacuum, then this is 0, or very small. So then you would have no drag. Like, well, cars cannot go through vacuum. Tell that to Elon Musk. It's the Hyperloop idea, where he wants to take a whole tube of 100 kilometers, basically like a subway tube, 100 kilometers long, pump out all the air. Because then no drag, no force being lost when you accelerate, when you move it. So also, if you want to make a car that goes really fast, it's really hard because the faster you go, the more drag is being exerted. The faster you go, the more force keeps you from going faster. Right? And so that means if I were to, for example, jump out of an airplane, I would die the same, I guess, with the same injuries, jumping from a kilometer up or jumping from 100 kilometers. You cannot take an airplane to go 100 kilometers up. But Felix Baumgartner, he was jumping from 40 kilometers up, and he just had the same parachute as somebody like grandma's jumping from 2 kilometers up. That's because he doesn't go any faster. Well, he went faster as there was less air. But once he gets into the 1 kilometer distance, the air drag is so high that it just slows him down all the same. The only problem is that he was going really fast in the beginning, so he got hot. But be that as it may, there is a concept of terminal velocity. It's not just an awesome movie. It's actually not an awesome movie. It was Wesley Snipes' movie, not a very good one. But the idea is that you will not reach higher speeds than, like, drag basically slows you down. And the faster you go, the more it slows you down, until all your force, all your gravitational force, is being converted or being eaten up by drag force. What happens if your drag force is as big as your gravitational force? You're stopping. You're not stopping, but you're not accelerating anymore. So that's terminal velocity. So we can calculate terminal velocity, right? Because all we have to do is make sure that drag force is equal to, like, terminal velocity will happen when drag force is equal to gravitational force, right? So we can put the two together and solve for velocity. And so we're getting that it depends on your cross-sectional area, density of air, and gravitational force, right? So that brings us to an interesting question, and that is, will an ant dying from a house falling from a house die? Right, so maybe a house is too short. Type in 101. Okay, you drop an ant from type A 101, and I'm claiming that it will reach terminal velocity. And I'm hoping that that terminal velocity will be small enough that the poor ant doesn't die. Why? Because gravitational force on an ant is really tiny, right? But the area of an ant is really tiny too. So I'm hoping that the two are kind of canceling out to something tiny, so that the poor ant will walk away. And the second question is, all right, fine, how about a horse? Okay, I managed to move a horse up to type A 101, which is hard, but they have elevators. Would a horse die when you drop it from type A 101? Why? You're like, sure, I've tried that before. And horses are not compatible with type A 101 drops. Why? It has a bigger gravitational force, fine, but it has a bigger cross-sectional area. Why do you think that an ant might walk away and not splatter like a horse on the pavement? So that brings us to one important simplification of animals in physics. Spheres. We're going to assume that an ant and a horse are just balls of meat. Okay? So let's start with that. So this is type A 101. And here we're dropping something. And we're saying this one is just a ball. Okay? So what does that mean? Well, you see, this one here depends on the weight of the horse. This one here depends on the cross-sectional area of the horse. I don't know how the two are related. But for a ball, for a sphere, I do know. Right? The mass of the ball is its density, of the horse, times the volume. Somebody remember what's the volume of a horse? Volume of a sphere? 4/3 pi r cubed. Where r is the radius of a horse. You understand why we're doing that for balls, and why we might be off by a little bit, because it's like a long axis on a horse, but it's short. So it might be more like an ellipse. Fine. So that gives me the mass. How about the area? I squared of a sphere, right? Because it's a sphere, but the cross-sectional area is a circle. Okay, so let's plug that into the terminal velocity. Terminal velocity would be 2 times m times t over c times rho times a. And c is, again, all the complexities of a shape go into c. So this is the drag coefficient. If you're into cars, you would know that the drag coefficient of a Formula 1 car is 0.04. And the drag coefficient of my Toyota is probably like 0.3. See a big difference between the two. The difference is I can put 5 people in my car, whereas a Formula 1 car is designed to minimize drag, right? So the drag coefficient of the sphere is about 0.5. And the density, this is the density of air, right? So that's about 1. And we don't care about those factors. We only care about why would a horse not walk away and might. So 2 times rho of our body or cube over c times rho times pi r squared. And I'm not interested in all the numbers. I'm only interested in the r, right? Because that's the only thing that distinguishes an ant from a horse. They kind of have the same density, I would guess, right? Probably the density of water. So I'm only interested in r. And so you see that this one goes like square root of r, right? I cancel this against that. So that means the terminal velocity of a body, of a sphere, but I would guess for any other body as well, depends on its size. The bigger something is, the faster it will fall. And that means that an ant would be safe, and a horse would not. And if you don't believe me, people have done experiments. I'm not going to show you a video on that. But I found a 1928 essay where he said that riding on the bottom, you can drop a mouse on a 1,000-yard mine shaft. That sounds borderline psychopath. But okay, apparently he found a mouse, dropped it down a mine shaft, and on arriving at the bottom, it gets a slight shock and walks away. So not only did he drop a mouse, he even watched it as it was arriving at the bottom and being like, oh, that guy's fine. But then a rat is killed, I understand that, and the man is broken. Not sure what. And a horse clashes. So that's all the information that you need to illustrate that problem. Terminal velocity depends on the size. For humans, the terminal velocity is about 150 kilometers per hour, meaning you falling without a parachute out of an airplane is about as bad as you getting hit by a car, by a really fast car. So there are chances for you to survive that. Well, you're gonna be broken, but you can make sure that you're landing feet down first, so that you're gonna absorb the shock in a slightly less fatal way than face down. I would still not recommend it, but there are reports. There are reports of people that have survived skydiving accidents. So terminal velocity works. But back to our problem. Okay, we were saying that those stones are moving, right? And I was claiming that wind is the only thing that we haven't accounted for. It's not animals. It's not earthquakes or something. Maybe wind. And so what these people, so this is real research. So the first part of the problems are from your lab, from your textbook, right? I just took it out of there. But this is pictures of real research being done really recently. We 5 years ago. So people were like, huh, this problem in the textbook, I'm going to go there, I'm going to measure what made it, what made it. So we're going to get, so they fitted, I think, 20 different stones with GPS trackers. And then they just had recorded the position of them and wind speeds and stuff for like a half year. They're like, well, would wind be able to do it? And so we could now claim that we can estimate if wind would be able to do that. So that's good. So we are now assuming that the stone is still the same, 20 kilograms, so it takes 160 Newton to how fast would your wind have to blow to make it move? All right? Well, is it reasonable to assume wind would do that kind of thing? Just to be, so that we start at the same number, we were saying that the force that has to be overcome to make it move would be 160. Okay. Would that be possible? You have 5 minutes. Just drawing it for my viewer. I have a single viewer now. It's a big decline from my 13 subscribers. It should not be that hard. It's just plugging everything into one formula, right? Or you don't remember the formula. Right. Just resolved it myself. Like I said, it's just putting in the numbers that we already have to equal the 160 newtons that would be needed to keep pushing. And so that would be 320 kilometers per hour. So that's a lot, because even if you have like a category 5 hurricane, you would only be 90 meters, 206, meaning you would need a hurricane to move those stones around, right? Not sure, but it actually turns out that that's exactly what happened. So these are the traces of the GPS trackers, so you can see that they're moving, and you can, so the one is the temperature, so that's what it goes like up and down and up and down. In the day it's really hot, at night it goes below freezing, and then you have the wind speed. So whenever there's like about 20 meters per second, 20 meters per second is 60 kilometers per hour. So that would be enough to make it move. Right? This is the acceleration of the tracker. So wind is enough to move that. Why? I mean, did we go? So we just said unless it's a Hurricane 5, it should not move. But they're saying strong wind gusts, but nevertheless, like not hurricane range wind would be enough to make it move. That's because one thing we didn't know was that actually there's ice in the Death Valley. In the night, especially in the night, it goes below freezing. There's enough water to condense and freeze, and so those ones are enough for it to slide. The kinetic coefficient of friction for ice is much lower than what we assume, 0.8. So it's actually wind blowing those stones around. So that's pretty cool. Right. So that kind of ends mechanics in, like we have described everything that we're interested in. We mechanics is the reason for motion, and it depends on forces, and there's a couple of forces that we have now played with. It doesn't really answer, like, mechanics, I feel, is not really answering the question as to why stuff moves. Like, because forces are interacting. Yes, but why are forces there? It's not really telling you the underlying mechanism. So actually, when I was thinking of designing this course, I was thinking of skipping forces and instead focusing on the underlying reason for forces, and that is energy. Energy would not have all these complicated components, wouldn't have to keep track of sines and cosines. Instead, we would simply give an object a number, one number, and then we figure out how that is related to motion. So let me introduce energy first. I mean, we have the concept of energy. Energy is something you put in to heat up stuff or make stuff flow. In our case, energy is a scalar that is associated with with an object. Okay. It's a temperature of an object, the speed of an object, it's how high an object is flying, or how much it has compressed its spring. All these things are related to its energy. And so the reason that we like energy much more than force is because there's one rule in energy, that is, energy cannot be lost. So if I keep track of all the conversions of energy, I can calculate the new state of an object without having to figure out how fast it moved, where it went, how forces were interacting on. So energy is like in the lectures video, I was describing it like a currency. It's kind of, you don't have to know where you spent the money. You're just interested in how much money is left at the end of the month. You know if you well, or have to ask mom for a raise. So we're going to start with one type of energy, that is kinetic energy. It's the energy of motion. And then probably next time we're going to introduce a second one, which is the energy stored in lifting something or in deforming something. So, and we're introducing the concept of changing energies. So that's more. Right. So the nice thing about kinetic energy is there is only one. It just depends on the velocity. So no matter if you have an electron or a black hole, if we're talking about the energy, the kinetic energy, it's always velocity and mass. It's the only thing that goes in there. So the unit of it is a joule, and that comes down to velocity squared times mass. So that's the right one. And yes, before we go there, we can derive how is kinetic energy imparted on an object, right? If we have mv squared, we know how where v comes from. It must have accelerated from 0. So that means that v is just acceleration times time, or over a distance. And so we can say that this velocity is just due to a force times time. And so we find that the difference in kinetic energies can be simply calculated without us knowing why, as you need to apply a force for a certain distance. You could also say, I need to apply a force for a certain time, but it just, then you have time squared. So we don't like that. We put it as a function of distance. So this means we provided force while pushing it. We call this concept of, we have to do something to make it move. Right? We are introducing work to give an object kinetic energy. If we didn't provide force over a certain distance, it would just stay there. It would be 0 velocity, meaning 0 kinetic energy. To make it go faster, you have to provide work. work is simply force times distance or acceleration of a mass times distance, which you use today. Right? So that means that we now understand why energies are so nice, because the final one is just different from the initial one by the work that has been supplied provided to it, right? So if no work has been done on an object, the kinetic energy is the same. Or the other way around, if I know how much work was done on an object, I can calculate the new kinetic energy. Yes. Okay. And so we're going to skip this one instead, because this one is just work times distance. What's the force? Force is the slope of work distance diagram. So that's why we like energy. So energy is work, right? We were saying the change in energy is work. And we're saying in an energy distance diagram, the slope is a force. Because force times distance gives me work. Right? So now you understand why I feel that that is more attractive. Because if I were to plot everything in a work distance diagram, you can get the forces just by taking the slopes. The three-dimensional work distance diagram, which I can draw, you still get the slope, right? So we wouldn't have to worry about trigonometrics. Not fine. So slope is reward, that is force. So we can do that with any kind of. So we're saying that work is force times distance. But what if the force itself depends on distance? So remember, we had a simple example of that, and that was a spring, where the force on the spring would be K times F. Right? So now, K times distance. So now I cannot say it's force times distance because the force changes at every point. Right? It gets harder and harder to compress the spring. That means I'm putting more and more work in to displace it by a centimeter or millimeters. So that means that I would now have to figure out how to get the work for a variable, like for a changing force. If this is force, this is distance. This is spring. And this would be a constant force. We're saying the constant force work equals constant force times distance. What would that correspond to? That's the area under that, right? Y times x. So if it was spring, can you get the area? I mean, we know this. This is D, and we know this one at a position D. This is K times. Right, so I know this length, and I know this height. Can I get the area from that? What's the area of height? 1/2 times height times base. Right? And that would mean that for this one, work would be 1/2 times K times distance times distance. 1/2 K squared. So I can get the work done. I can get the work that has to be done to compress the spring, and it gets higher the more I compress it. And so, oh, right, we have enough time. Hooke's law. So we have introduced the spring force, but I haven't had time to ramble about Hooke's law. So this is named after Robert Hooke, who who's older than Newton by about a generation. So he was alive when Newton was like, all mechanics is mine. And Robert Hooke is like, the whole concept of forces is something that I did, okay? And so Newton was very angry about that. And so there are several stories about that. Robert Hooke apparently was very short. And so when Newton said his famous, if I got to see farther, it was because I was standing on the shoulders of giants, which for us epitomizes like collaboration in science, right? You can only get as far as, like, you're only advancing science a little bit, and you're doing it because people before you did good work. But what Newton meant was I was standing on the shoulders of a really tiny guy. Okay? So again, Newton was not a very nice person. The other thing was that Robert Hooke was the Chancellor of the Royal Society before Newton. And so we don't know how Robert Hooke looks like. There was a picture in the Royal Society of Robert Hooke, but Newton had it broken down, had it removed. So again, just because of his vengeance, we lost history. But at least we got in the books now. Even though you will see that a lot of the considerations about gravity that we're now calling like the epitome of Newtonian mechanics was actually done by Hooke before Newton did his mechanics. So Hooke's law is, I think, too little credit to Robert Hooke, but at least he got that. So we can use it to calculate the work. And yeah, okay. So we're going to use that little problem. So that tells you that you remember I was giving you position time diagrams, velocity time diagrams, acceleration time diagrams. I said that's useful because they are interrelated. So this time I gave an acceleration distance diagram, and I would like to know how fast is I'm only interested in how fast is the particle after it has gone. This acceleration, that acceleration, decelerate, come back up. You understand? It goes faster, it goes slower, it goes slower, and it goes back to zero acceleration. Right? So what I would like to know is f, how fast at 9 meters. I give you 10 minutes, and then we can still resolve it before we start. Oh, 10 minutes. Good. from the F. I mean, just as I don't know, maybe a hint, I was not introducing force distance diagram and gushing about how awesome they are to then give you an accelerations distance diagram to have you start kinematics, right? How are the two related? What I'm saying is, can you make a force, can you make this diagram into a force distance diagram and somehow apply my idea of calculating work to calculating speed? Right? Otherwise, this would be in chapter 4, not in chapter 7. Guess I'm going to answer my own question. I can simply make this one into a force if I multiply mass times acceleration. That means 12 here, minus 12 there. That's all the changes. 6, I think. Speed. So you're asking why don't I want to know the particle's velocity? Because speed is a magnitude and direction is the direction. So I could, if I ask what's the particle's velocity, then you would still have to give me the magnitude and direction. It goes 5 meters in this direction. So either way, particle speed and direction is the same thing as particle's velocity. It's just that I want to be, well, to remind you, if I imagine we get like 6, there's two things. 6, you need a unit, meters per second, and you need a direction. I ask you for velocity. So I wanted to just remind you. I'm not really
No problem, yes.
So everybody's already done, or you have no idea how to start? You're done. No idea how to start. Okay. Well, so what I was saying is, if I know the work being put into a system or given to a particle, I can get its kinetic energy. So I know that this one started at 0 from rest. From rest. So it had kinetic energy of 0, right? It was stuck. It had a 1/2, like kinetic energy is 1/2 mv squared. So its initial energy is 0. So what's its kinetic energy afterwards? Work. All the work that I'm doing on it. That's the beauty of energy. If I keep track of all the work, I will know its total energy increased by that much. Why would that be interesting to me? Because I also know that K final is 1/2 mv final squared. Did I put squared? Yes. So that means if I wanted to get the final velocity, I would just get 2K final over m. So now the only question is how do I get K final? Work. So how much work have we put in? Well, we put in positive work, so we made it go faster, and then we take away negative work. And so is this area the same as that area? If they were, I put in work, I take out work. Like, imagine those two areas were the same. I'm not sure that they are. If they were the same, then I put positive work, then I take out work. If it's the same amount, then I haven't done any work. The total work done on the system would have been 0, meaning the final velocity would be 0. I speed it up with as much energy as I slow it down. That was also a question of today's quiz, right? How long does it take for it to slow down? Well, how much work did you put in to make it go faster? That's how much work you have to provide to make it go slow, that you can take out to make it go slow. So in this case, we would have to calculate the area of this one, that's how much faster it goes, and subtract the area of this one, that's how much slower it goes. If you squint your eyes hard, you'll see, so there's a triangle here, there is a square or rectangle here, and another triangle. So these are my two positive triangles, and this is a positive rectangle, right? So this one here would be cancelled against that one there. Don't have to calculate it. This one here would be cancelled against that one there. Now the only question is, are these two squares the same? They are, then it cancels out. And unfortunately they're not. But this is 2, this is 3. So that means this is the only slither that is left. There's a little bit of additional positive work that was done that is not being cancelled out by the negative. So this would be 1y, and it would be 12 Newton. Right? So that means that my work would simply be force times distance is 2 over mass. And so force times distance is 12 times 1, 24 over 2. 24 over 2 is 12. So I would get this is square root of 12. 3.5. Yes, I knew that. 3.5. Right. So is that easier than if I had calculated the acceleration? I would have had to calculate the time, right? Because I don't know the time, I only know the distance. And then I would have to calculate it goes faster, it stays the same velocity, it slows down, it stays the same velocity, and it goes faster again. It sounds, oh no, wait, that's not true. It would go faster, only here it would stay at the same velocity, and then it would go slower. So I feel that that is not an easy way of calculating the same thing. So we see the potential of energy in making our life easier. We didn't have to worry about acceleration distance, like a direct fraction. We didn't have to calculate with vectors. We just had to integrate over scalar. That seems more achievable. Right, so we're going to cover potential energy next time as another form of energy. Questions about what we've done today or what we're going to do next week? Any concerns, problems, questions? If you have questions or problems that you don't know how to phrase or you need some time to think about it, send me an email. Okay? My email is Mario. I think if you're making a note, you can put a note on Google. I am hesitant about that because as I post, like there's still people that are catching up. And so as long as I don't post the solutions to the quizzes, but you should be able to see, can you see the outcome of the quiz?
I can just see my outcome, not really what I got wrong.
No, that's true. Yes. Yes, but you do see your points.
Yeah.
Okay. Well, but I mean, these questions are fairly simple compared to the harder ones in here, are they? Or so you would like to have more solutions, or just like solutions of those ones, or you just want more problems to solve? Either way. Okay. I'll think about making those. It's just administrative task. All right. If there are no other questions, thank you for coming, and see you next Thursday. Yes, please. It's gonna be at the beginning of November, but I will tell you 2 weeks in advance. It will not be like surprise. The quiz is a little longer. Oh, welcome. Yes. You're sure. How do you get How do you get the points? So there's a point based on recitation. It's all about going through the to get to the answer. So if you have the right answer, the quiz is inside the recitation. Initial So you also say the correct cannot be more meaning, give yourself a so that's how we interacting, or how I keep track of your answers. And then the quiz is this. Sorry, yes, it's good. No worries. We're it's going to be a lot more. In the student group. Or in the general chat. Yeah, we'll keep track. But for next time, just so that you can chat with people in the group as well. Because while we were online, only available online stuff if you wanted to talk to them. Alright, welcome to Taiwan. Yes, I would. So I thought I had uploaded the recitation last week's recitation. So there should be the recitation. I'll put that. Yes, because you're supposed to, because you were not here, right? So same thing. You're listening to me, Susan, just look at the lectures. Yes, only Tuesdays we're having online class, and then Thursday. This is only for 60 people, like only about 40 here, because the other ones are choosing to just take midterms and finals. So if you're confident in physics, you can simply skip the whole thing and just be here for midterms and finals. And then those grades would be 50-50. If you're attending recitation, then the quizzes and in-class participation would be 50, I think 50%, and then the better exam is 75 and the worse 15. So one is kind of more unsure about physics. I will make sure. I will check your grade. I will pick the better. So even if you're in recitation, it's stellar in like midterm final. You have those 100 points there, 80 points in quizzes or something. I will choose the better. So you don't have to choose. But if you're confident,